Welcome to the 7th video in the Fortitude.tech Python package walkthrough. In this video we'll be going through some exponential decay modeling functionality. And a funny side note is that I actually don't believe that this is a good risk model. The reason that I decided to include it in the package is to prove a point. Because I heard that some institutional investors were still paying software subscription fees for something like this. So I wanted to show them that it's not worth paying for. So I spent a couple of hours implementing the functionality, testing and documenting it, and then releasing it. So if you are an institutional investor and you are still paying for something like this, then there is no reason to continue to do so. You can save that money, and then in the best case you can come talk with us because we have something that is actually worth paying for. Alright, so as always we start at the front page of the repository and then navigate to examples. So here you can see that example number 6 has something with exponential decay in it. The data that we work with are FANG stocks and S&P 500. So here we first import the package that we need, and in this example we do some plotting. So we use Seaborn Matplotlib and then Y-Finance to get the data. So here we get the data that we need and just show some of the first observations. After that we make a plot where we normalize the first point to 100 to compare how these stocks have performed. And here we can see that Netflix has really exploded during this period. After that we compute the return for these data and show some statistics using this simulation moments function. So here you can see that these returns have kurtosis that are very high and they also have some skewness. So if you are trying to fit something like a normal distribution to this data, then it will be very hard. And this is why that we suggest that you do something else that is actually able to capture all these nuances and these statistics better. After that we plot some kernel density estimate of the returns, and you should remember that these kernel density estimates, they do some smoothing, so they look quite nice compared to, for example, a histogram. Finally we do some portfolio optimization. So here you can see we just compute the historical means and the historical covariance matrix. So this is what we need for mean variance optimization. We implement some constraints that this is a portfolio where you must be 100% invested in S&P 500, and then you are allowed to have long short exposures in the individual stocks. So you can imagine that this is some overlay portfolio that you are trying to optimize. So here we initialize the mean CVI and mean variance classes and use the efficient portfolio method with a return target, which is just the average of this historical expected returns. And of course this is just for illustration, I had to come up with some return target. Okay, so then we collect it into one data frame and plot the results. So just to see how the portfolios they look here. And you can see that there are some differences, but they most of the time they still point in the same direction. Okay, so then we compute the P&L distributions for the portfolios and again plot it with a kernel density estimate. And since we are quite restricted in what we can actually do, then of course the difference in these returns will not be very large. But we also plot here the historical performance with daily rebalancing. So you can see that most of the time the SIBA portfolio is actually doing better on this sample than the variance optimized portfolio. Finally we just compute some statistics for the portfolio. So here we verify that the return target is satisfied, and we verify that the variance is lower for the variance optimized portfolio than the SIBA optimized portfolio, and similar that the CVI is lower for the SIBA optimized portfolio than the variance optimized portfolio. If these things were not correct, then we know that something went wrong. Okay, so now we get to where we actually use this exponential decay functionality, and there are two functions. So one is to compute the exponential decaying probabilities instead of using just uniform for the historical observations, and another one is to calibrate a normal distribution with these exponential decay probabilities. So basically if you have calibrated normal distribution, then you are able to generate more new samples with a new mean and covariance matrix. It's not something that we recommend using because of course, we argue that mean variance optimization is not really good to approximate real world market behavior that you can read about in these articles. So yeah, we encourage you to do some more sophisticated risk modeling if you want to increase the sample size from the historic observations that you have. So here we use this exponential decay props function. So basically what it does is to give us a probability vector with a half-life parameter. So in this case we say that we have in total t observation, and then we want the half-life to be a fifth of t. So basically what this means is that the probability that you assign to the latest observation will be half of that, or twice as high compared to the scenario that you have a fifth back in history. So to see this, it's actually easier just to plot the ratio between the different probabilities, so you can verify that you understand how this half-life parameter works. Then finally we use this normal exponential decay calip. So basically what it does, it's the same thing with first computing this probability vector with exponential decay, and then it computes the mean and the covariance matrix. So this is what happens under the hood, and this is what we show you here where we verify that the two different methods give the same thing. So you can see that whether we use the exponential decay probabilities and then compute the means and the covariances manually afterwards, or the function, then we get the same results. So it's really up to you what you want to do. If you want to continue working with CVAR optimization or entropy pooling, then you can use these exponential decay probabilities directly. If you want to simulate from a normal distribution, then you can use this exponential decay calip function here. All right. So now we just want to repeat the analysis that we did before with portfolio optimization and then see how it looks. So here you can see that we specify a mean CVAR and mean variance class, where basically for the mean CVAR we specify a new probability vector, and for mean variance we use the new means and the new covariances, and then we optimize with the same expected return. So here again we look at the portfolios to see how they are, and in this case it seems that they become even more similar, because now we are giving more weight to fewer observations than before. If we plot the P&L distribution, then we can see also that it's quite similar for the daily data, and if we plot the historical performance, then we also see that there is a quite significant overlap. Finally, we recompute the expected return and the risk to see that we have optimized this in a correct way. So here again we see that the expected returns are of course satisfied. We see that the variance portfolio has a lower variance than the CVAR portfolio, while the CVAR portfolio has a lower CVAR than the variance portfolio. So this is as we would expect. So here some final comments are that I think that you should try to explore this example further. So try to do something with a longer horizon, with less frequent rebalancing, because my experience is actually that these things become more interesting to work with. So the differences between variance and CVAR will become more pronounced when you work on a longer horizon. Because if you are doing something with very frequent rebalancing and in a restrictive investment universe, then by construction the differences in the allocation is not going to be very large. All right, so this is the end of the walkthrough of the 6th example. And as always, if you like this package and if you like these videos, then I encourage you to give the repository a star, and then I hope to see you in the next video.